Let's talk about the third point, the basic properties of determinants. So the first property is the interchange of rows and columns does not affect the value of a determinant. So that means that we can calculate A or A prime. So the determinant of A and A prime are the same. So for example, if A is A, B, C, and D, and A prime should be A, C, B, D, right? And we can find that the determinant is exactly the same. So this is property 1. And property 2, the interchange of any two rows or any two columns will alter the sign but not the numerical value of the determinant. So for example, so this is a matrix 1 and this is matrix 2. So we can calculate the determinant of this matrix by expanding from the first row, right? So it should be 0 times its adjoint matrix or subdeterminant. So it's 0 and then minus 1 times this matrix and plus 3 times the subdeterminant. So it should be minus 26. I just use the general equation for the third degree determinant to find out the determinant of this matrix. And so if we we interchange the first column and the third column. So the first column is now the third column, and the third column is now the first column. So they should be 3, 1, 0, 7, 5, 2, and 1, 0, 3. Right? It becomes the second matrix here. So if we interchange the two columns, we can find that using the same method before to find out the determinant. And we can find that the determinant is the inverse. Is the same numerical value but with the different sign. Right? It should be positive 26 of the first determinant. And also, if we interchange the rows, for example, the first row and the third row, it should be the same result, right? The determinant will change from minus 26 to 26. So if you interchange any of the two rows or columns, it will not change the absolute value, but it will alter the sign of the determinant. And if you interchange twice, right? If you first interchange the rows and then interchange the two columns, so the determinant will be the same as original, right? Because you interchange twice, right? You interchange once, so it will alter the sign, but if you interchange twice, then it should be the same number as before, right? So this is a property 2. And property 3, the multiplication of any one row or one column by a scalar k will change the value of the determinant k-fold. So look at this determinant, Ka, Kb, C, D. Right, so we multiply K times the first row, and it becomes Ka and Kb. So the determinant of this matrix should be Kad minus Kbc, right? And then it should be K times Ad minus Bc. And Ad minus Bc is just the determinant of this matrix A, B, C, and D. So we can see that the determinant of this matrix is just a K times the determinant of this matrix. So it means that if we multiply K times of any row, right, any one row, only one row, right, one or one column, and so the determinant will be multiplied by K times, right? However, if we multiplied all the rows of the matrix, then it's a different story, right? So the determinant will change by K to the n times, depending on how many rows in your matrix. So for example, in the second example, the matrix becomes Ka, Kb, Kc, and Kd, right? We multiply all the A, B, C, and D with K. And so the determinant should be K squared, right? Because it's K squared AD minus K squared BC. So the determinant should be K squared times AD minus BC, right? And AD minus BC is the determinant of this little matrix. So we can see that it's not K times anymore, it's K squared times of the original determinant. Right? Because you have two rows here, so it's K squared. And if you have a lot of rows, it will be a higher order of K, but it's not the original A, B, C, and D, right? So only if you multiply one row or one column of the matrix can you get the K times of the determinant. But if you multiply two rows or three rows from all the rows in the matrix, then you cannot get K times, but K squared, K cubed, then K to the n times of the original determinant. Okay, and also you have to know the difference between Ka and K times the determinant of A. Right, so A is a matrix, right? So K times A means we multiply all the elements in the matrix A with the scalar K. So it's a matrix multiplication, right? We multiply the scalar K with all the elements in A. So that means that we multiply all the elements in the matrix A using the scalar K. So all the elements here are K times before. Right, so this is a multiplication of a scalar and a matrix. But the second one, K times the determinant of A, is totally different from multiplication of a matrix. Right? Because in the second example, you multiply K, the scalar, with the determinant of a matrix. So based on property 3, the result should be K times any one row or any one column of the original determinant. Right. So we cannot write K and K here, right? Because it's a determinant. And so if you multiply K before that, it means that you can only change one row or one column of the original determinant. But you cannot change all of that. Right? If you multiply all the K's and to find out the determinant, then it should be K to the m squared. Sorry, K to the m, right, times that. So it's based on property 3. And also you can write this matrix as, so it can also be written as Ka11, Kam1, then A1n, Am, right. You can change any one row or one column of the original determinant if you multiply only one K in front of that. Right. So here it means you multiply K to all the column to all the elements in the first column. Right. So these two things are equal to each other, but not multiplying K for all the elements here. So that's the difference between multiplying a scalar with a matrix and multiplying a scalar with a determinant of a matrix. And property 4, the addition or subtraction of a multiple of any row or column to or from another row and column will leave the value of the determinant unaltered. So it simply means that, for example, here we have this determinant. Right? You can see that for the second row, it says C plus KA and D plus KB. And A and B are just the element in the first row, right? A and B. And for the second row, it just means that there's another two numbers, C and D, but each of them is added by K times of the first corresponding element in the first row. Right, so based on property 4, the addition or subtraction of a multiple of any row to another row will leave the value of the determinant unaltered. So if we want to simplify this determinant, maybe we think it's a little bit complicated, so we want to simplify that. What we can do using property 4 is to multiply the first row K times and then subtract the first row from the second row. Right, so the first row will become KA and KB. The second row is still C plus KA, D plus KB. We first multiply K times the first row and then subtract from the second one. So the second row becomes C and D, right? Because we have already subtract the altered first row from the second row. So the second row becomes C and D, but the first row is still A and B, right? So this determinant is the same as this determinant. A, B, C plus KA, D plus KB. The determinant of this matrix is just the determinant of A, B, C, and D. Because from the complex matrix to the simplified matrix, we can multiply K times of the first row and then subtract it from the second row, and to get this simplified version of the determinant. And these two kind of determinant are the same. Right? And also, when we multiply K times of the first row, we don't actually change the first row. We're just using the property 4 and to simplify the determinant, but we don't actually change the first row. What we want to change is the second row. So second row will change and to be simplified, but the first row is still the same, A, B as before. Okay. So the two determinants are the same. So this is AD minus BC and this is AD minus BC. So they're the same. So this is property 4. And next time when you see a very complex matrix like this, you can simplify this determinant using property 4. Right, so this becomes minus Ka, this is minus Kb, and the result will be the same as before. Okay, so this is property 4. And property 5, if one row or column is a multiple of another row or column, the value of the determinant will be 0. So for example, if our matrix is like this, 2A, 2B, A and B, so the first row is just twice this of the second row. Right, so if this is the case, then the determinant will be just 2AB minus 2AB, which is 0. Right, so this is similar to what we have talked about, the linear independence case. So in this example, the first row and second row are linearly dependent because we can represent the first row using the second row. Right, the first row is just twice of the second row, so they are linearly related to each other. So in this case, this matrix, if we change that into a matrix, this matrix is not linearly independent. Right, the rows are linearly dependent of each other, and so the determinant will be 0. To reflect this kind of linearly dependence of the rows. Right. So the second case, if the two columns are exactly the same, right? C, C, D, D. The first column is C and D. Second column is also C and D. So the two columns are exactly the same. So that means that the two columns are linearly dependent of each other, right? Because we can represent the first column by the second column, right? Because they're exactly the same, so they can be represented by each other. And if this is the case, then we call that linearly dependent column vectors. And if this is the case, then the determinant is 0. It means that the two columns are linearly dependent, right? And yeah, that's it. So determinant is CD minus CD, which is 0. And we can also solve this kind of question by using the property 4, because this for this determinant, we can simplify that by multiplying twice the second row and then subtract it from the first one. Right, so the first row will become 2a minus 2a, and then 2b minus 2b. Right, if we want to simplify that. So the first row will become 0, 0, and the second row doesn't change, it's a and b. So determinant is 0. And for the second one, because the two columns are exactly the same, so we can simplify this determinant by subtracting the second row from the first row. Subtracting the second column from the first column. So the first column becomes 0 and 0. Right? The second column doesn't change, so it's 0. So in either way, we can find out that if one row column is a multiple of another, then the determinant is 0. Okay. So here we can see the determinantal criterion for non-singularity. So it's based on property 5. Right. In property 5, we know that if one row or column is linearly dependent of another row, that means it's a multiple of another row or column, then the determinant will be 0. Right? We say that the matrix is not linearly independent. And if the matrix A is not linearly independent, then we cannot solve the x vector in our equation system. So here, for our equation system, ax equals to d. As I said before, if you want to solve this equation system, then x is a inverse times d, right? And so that means that if we want to find out a unique solution for x, we have to make sure that A inverse exists, right? And A inverse exists means A is non-singular matrix. And it means that the rows or columns of matrix A are linearly independent of each other. And if the columns or rows are linearly independent, it means that the determinant of A cannot be 0. Right? So here this is our logic. If you want to find out if there's a unique solution of x, there are two ways that we can do this. First, we can check the rank of A to see if matrix A is a full rank. Right? So if matrix A is full rank, that means that the rank of A equals to the total number of rows or total number of columns of A. Right? If this is the case, it means that A is a full rank. And in this case, A inverse exists. Right? A inverse exists. It means two things. And second, we can check the determinant of A to see if it is 0. If it's not 0, then A has inverse. If it's 0, then based on property 5, we can see that A is not linearly dependent. A is not linearly independent. So the A inverse does not exist. So two ways that we can find out if there's a unique solution of X. Right, the first one is we check the rank of the coefficient matrix A to see if A is full rank. And the second one is we check the determinant of A to see if it's not it is not zero or not. Right, so there are two ways to find the answer. Okay, so here's the example. So this is the example of the equation system. Right, so this matrix is A. It's a coefficient matrix. This is a vector X. This is our D vector, right? A times X equals to D. So this is our equation system, and our goal is to find the X, right? Find X1, X2, and X3. Now D are just a constants, right? So D1, D2, and D3 are constants that we already know. And the only thing that we don't know is the X vector, right? So in this example, we want to find out if there's a unique solution to X. So that means that we want to find out if matrix A has inverse or not, right? So if I want to find out if the matrix A has inverse or not, we can check the determinant of matrix A to see the result, right? So this is the matrix A, and the determinant of A is 0. Why? Because we can see that the second row here, 15, 20, and 10, are just exactly 5 times the first row, right? 5 times 3 is 15, 5 times 4 is 20, 5 times 2 is 10. So the second row is just a multiple of the first row. So based on probability 5, if one row is a multiple of another row, then the value of the determinant will be 0. So that means that the determinant of A is 0, since the second row and the first row are linearly dependent of each other, right? The rows are dependent. And you can check the determinant of A by calculating that yourself. So we can simplify this determinant from the first one to the second one. So the second row are all zeros, right? So from here to here, we subtract 5 times the first row from the second row. So this is 15 minus 5 times 3 is 20 minus 4 times 5, right? So this is 10 minus 5 times 2. So we subtract 5 times of the first row from the second row, right, based on probability 4. So we don't change the first row, actually. We want to simplify the second row. So only the second row changes, and the first row doesn't change, right? We only just use the first row to subtract from the second row. So we don't actually change the first row. So the first row doesn't change, but second row changes. Right? The third row, we don't move that. So the matrix becomes this. And the determinant of this matrix is really simple. Right? We can expand from the second row. So everything is 0. And so the result is 0. And the determinant of A is 0. So there's no unique solution for X in this example, since the determinant of A is 0. And here's a little note. If there's row independence of A, then it also means that there's a column independence of A. So it means that for A, if the three rows, for example, in this here, if the 3 rows are linearly independent, then the 3 columns are also linearly independent. right? Or if the three columns are linearly independent, I mean there's no multiple relationships. There's no one column that's a multiple of another column, right? So that's called linearly dependence. So if the three columns are linearly independent, then we will also know that the three rows of A are linearly independent. Right, so from one thing we can know the other, and from the other we can know the first one. So the relationship is if and only if, right? So this statement, the first statement is the necessary and sufficient condition of the second one. Or we can so from the row independence we can know the column independence. So they're the same thing. From one thing we can know the other. Okay, so here's another example. Does the equation system possess a unique solution? So in this example, it doesn't just give you the matrix A, X, and D, but it gives you the equation system. So the first thing you need to know is to write down the matrix A, matrix X, and a D from the equation system, right? Since it's not given. So we know that A is a coefficient matrix. So A is just the gathering of all the coefficients in the equation system, right? So it should be 7 minus 3 minus 3 and 2, 4, 1, right? Just extract the coefficient from the equations. And 0, right? Since there's no x1 here, that means that the coefficient of x1 is 0. And this minus 2, minus 1. And the x vector is just the unknown three vectors, x1, x2, and x3. And then D is just a constant, so it's 7, 0, and 2. Right? So first thing is that you have to write down what is A, what is X, and what is D from the equation system. And then we'll check either the rank of A or check the determinant of A. Right, so here we check the determinant of A. So the determinant of A, the easiest way to find out the determinant is to expand from the third row, right? Since we have a 0 here, so we can get rid of this term. So the determinant of A should be the minus sign before the minus 2 times the subdeterminant, right? Because the minus 2 is a 3, 2, right? The third row and the second column. And 3 plus 2 is odd number. So we have a minus 1 before the minus 2 term, right? And then plus minus 1. So this minus 1 is the coefficient here, right? It's element 1, some element here, right? So plus minus 1 times the subdeterminant. So this should be minus 8. And it's not 0. So the determinant of A is not 0. It means that there is a unique solution, right? If the determinant of A is 0, then there's no unique solution. And if it's not 0, that means that A has an inverse. And so a unique solution will exist for this question. Okay.